I hope I'm audible. And my screen is visible as well. So in today's class, we'll gonna learn about the important topic in computer programming, that is game theory. And in today's class, we will be learning starting with GMDP, we'll looking at some standard question. Then we'll move on to the game theory part, like what is in game next, like in second half. So let's start with the first half. Okay. So before starting, I have a question. It is, suppose imagine a game. There are 10 stones there on the table, and the rules are simple. Two players play alternately, and on each turn, player can remove one or two stones. The player who removes the last one wins the game. Right? And this is the important line, that is, both players will play optimally. So suppose this is a game like this. So there are 10 stones placed on the table. So two players are playing this game. Those Alice and Bob, A and B. And in one move, uh, Alice can pick one or two stones. Right. So she can either pick one stones, or she can either pick two stones at a time. Right. And after Alice move, the Bob will play his moves. And his moves are same. He can either pick uh, one stones from there, or he can pick two stones from there. Sorry, there. Else, if Alice pick this move, then we have two more options. Like he can pick either one stones from here or two stones from here. Right, and game will end eventually at when players have no moves to play. Right. So this is a basic game, but if you think in a greedy way, I will not able to solve it. Suppose in the game there are 10 stones there. So if you consider for three stones only, so let's try and for only three stones are there, then how will we both players play this game? So if there are three stones in one move, let's take a different color. In first move, Alice can either pick this one or can pick this two. Right. So now if Alice pick the green one, then Bob can pick the another one or this one. Right. And if Alice move was this, then Alice can pick like Bob can pick this one. So irrespective of what moves Alice play, she will eventually get to lose. If you clearly look into the current case, because after Bob move, there is no element present. So there are no valid moves present for Alice. So for any, if Alice will go with this green one or this red one, she's gonna move on both way, right? So, and if I take example of four, in this there are multiple ways, right? So we cannot determine the game by looking at the numbers of stones there, right? So we must have to explore all the possible cases. that we usually do in dynamic programming. And we need to take care of all possible cases, and then we need to find the if our player can win the game or not. So, and the same question I have taken in the next slides. So we'll be looking there with it, right? So in the game state classification, there are majorly two parts. First is winning state, and second one is losing state. So what is winning state for a player? Winning states is a simply uh, if any move leads the opponent to a losing state, then the move can be called as a winning state. So if I show you in this step, uh, suppose this step, like after this one, the other player doesn't have any move. So this can be considered as winning state for Bob, not for Alice, because after this move, there are no possible moves for Alice. So this move is a winning state for Alice. And similarly, this move is a losing state for Bob, like Alice. This is a winning state for Bob and losing state for Alice. So if I write here, it is a losing state, losing state for Alice, and the winning state for Bob. Right. So this is it. And so let's move into the question part, because this topic is majorly based on some standard pattern. So first question is predict the winner. So this game is simple. There will be a array nums, right? And two players will be playing this game. Same from the array question. And rule is simple. Player will either pick the first element of the array or the last element of the array, and then he will removing the that element that they are picking from the array and adding that number to their score. And the player which ever have the more score or better score is gonna win. Otherwise, he will not lose them. So if I take the test that is 152. Suppose this is 152 is there. So game is simple. There are two players playing, P1 and P2. Initially, their scores are 0, right? And Alice will be moving first, as always. And they are also written, both players will play optimally. So player 1 can either pick this 1 or this 5, right? So if he went for the 5, so score will become 5, right? And this element will be deleted from the array. Now player 2 can pick 1 or 2, because this one is extreme at present at the extreme left, and this is the ending element. So he can either pick 1 or 2. So let's suppose he's picking 2. So his score will become 2, because uh, the 2 will be added to his previous score. And in the third move, the player 1 will again have to pick one element. There are only one element left, so he'll have to pick the remaining element. So its the score will become 5 plus 1, that is 6. So you can clearly see player 1 has a greater score than player 2. So the winner will be player 1. In the current test case, it is a simple array is given. The size is 3. That's why we brutally solve this question or by observing. But if our array length is bigger, then we need to explore all the cases, right? Because if we try to solve it greedily, suppose I am taking a case and try to solve it with greedy approach, like picking the best from the left and right. So we may fail because suppose our array is like this, 2, suppose this is 100, this is 1, this is 3. So if you think you pick the maximum among extreme left and extreme right, so you might pick this 3 one. So this can be also 100, and I'm making it 10. So in this case, you will pick the this ending one because in the greedy approach we pick the maximum element, right? So we'll pick there one will pick 3, and that element will be get erased from the array. But for the player 2, we have given a very greater number, very large number. So he can be easily win the game because he can pick the 100 one. So by greedily, you cannot solve this type of problem. You need to explore all the cases. So we need to define a recursive function for this for solving this problem. So the approach is here. So for DP or recursion, we require like first we need our states, right? So for the current question, our state is simply the like we can easily observe that we are using first index or last index. So we need to use that as a state. So we have a state like I and j. And if I talk about the base cases for this question will be suppose our array get completely erased. So if our I becomes greater than j, so in that case, there will be no element left inside the array, right? So that can be our base case. So we can write our base case as if I is greater than j, we can return 0, right? And third is we need to design our transition, right? So for transition, for this question will be for suppose we are playing a game and we want to win the game, and we can only control our moves, right? So how will we uh, optimally play the game such that we can surely say that we will gonna win the game? We can do it by like suppose we have 3 choices. We can go either in this direction or this direction or this direction. So we'll be picking that direction. That will force the force my opponent to lose the game. Like uh, like in this case, we can assume like we'll picking that direction that keeps the lower element to our opponent, right? That can be used in this problem. So if I show you the approach, it is like this. So let me first take an example and try on the tree. Like I previously drawn the okay. So suppose this is a question in which we have 3 elements are there. So in starting, we have we can go with the picking with the first element or the last element, right? So we have 2 cases here. here, let me first write this. What are these? Okay, so it will be better. So inside the recursive call, I am passing first total. Is T represent the total sum of all elements, right? And the second one is I for tracking the first element of the array, and the third one is J for tracking the last element of the array, right? So now, if we want that, uh, what will be the maximum score we can get between 0 and, like in this case, 2 index, right? So that's why I'm passing 0 and 2 here. So after passing this inside the recursive call, uh, the player can choose two directions. He can either pick the first one or the last one. If we pick the first one, so our I will be incremented to the next index. It is 1. That is why I am writing 1 here, right? And if we try to pick the last element, so we need to decrement the j, right? So that is why I decrement the j from 2 to 1. Right? So this is the first move, right? Now the question is, this is recursive call not specified for player one. This is for both the players because both players will be playing optimally, right? Now, suppose let's come to the base case first. If our I becomes I equal to 0, then our next move will be uh, I plus 1. And if I and j are equal, I plus 1 must be greater than j if we move any distance, or in this case also, it will be greater than j minus 1, right? So this is the base case. So it will return 0. And this is also base case. It will also return 0. So we'll be picking the minimum among the base cases. So here both are same. So we can pass 0, right? So now, if we see the code, the if we are returning a base case here, and we are picking the minimum among the, suppose a game is going, right? And we give the chance to opponent to play his moves, right? So he will always pick the move that uh, ensures him that he will get the maximum run. But if I have authority, I will play that move that ensures that opponent will get the minimum score. That is why we are taking the minimum, because our move is this, right? And we are exploring all the moves for opponent and then returning our answer. So now after returning 0, uh, here our total is 4 and here total is 2. In this case, it is also returning 0. So now we will have 4 and 2. So we'll be picking the minimum. From here, we will return 2, and from here, we'll return 4. So as we are picking the minimum one, so we'll pick this one, right? And we'll be subtracting because it is the move of our opponent. So we have to subtract it from our total because we are not picking that element. So our total up to this is 6, right? Let me refresh it. So, uh, in- okay, yeah. So, where the, like we need to pick the minimum, right? Because this is the opponent's one. So we are picking the this one because two is minimum from four and two, and then we have to subtract it from our total, that is six. Now this becomes four, right? So this will return four from here. And similarly, uh, if we do the calculation from here, we will return three. And among four and three, three is minimum. So we're gonna pick the three one, and we'll subtract it from our total, that is nine here. So if we subtract nine from like three from nine, we have six. So between 0 and 2 index, we can have maximum score, that is 6, right? So if we try to find it by observation, so player 1 will pick 4 first, so its score become 4. Then player 2 will pick either 2 or 3, so he will be going with 3 because 3 is greater. So player 2 will have 3 score. And again, there is only one element left. So player 1 will eventually pick the last element. So his score will become 6. And 6 is our answer from the this dynamic programming tree. So this is the approach. And if I talk about the time complexity for this question, so we know that for TP question, time complexity is of number of states into number of transitions, right? So for this question, there are two states, and transition is like constant because we are picking uh, from the two, either left or like extreme left or extreme right. So the time complexity will be close to O of n square. So for the given constant, it will easily pass, right? And we use the BP array for storing the states. So it will reduce the time complexity from exponential to the linear one, that is O n square. So this is about the first question. Now let's move to the second question. That is stone gate. This question is similar as same as the first question, which we tried to solve using DD1, and we were not able to solve the question. So let's look into the TP approach now. So suppose array is given. Now in this question, the element value is not used, so we can write any arbitrary number. Because we can only pick number of elements. Right? We have not to deal with the value of the element, right? So what is the DP approach of this question? So in the like player one, start the move. P1. So we can either pick the first one. So we can either pick the first one or first and second both, or first, second, and third book. Because in this question, we can pick either one stone, two stone, or three stones, right? And we need to determine if Alice will gonna win this game or Bob will gonna win this game, or the game will tie. So, Alice can pick one, two, or three elements one at a time. Now, after picking any element, what she want is she want that she will pick uh, that case such that the opponent will have to pick like will go to that. Like, let me try and discuss for better understanding. Suppose first let me write the states for this question. If I go to the code part, for this question, states are only index. Because it is only dependent on the index as we are moving forward only. So suppose here, like this will pick one element. So his score will become the in this question score is not needed. Wait. Okay, okay. This question is a little different. So let me read the question once again. So Alice and Bob playing the games with the piles of stone, and there is some value associated with the stone, and each player can either pick one, two, or three stones from the first stones in the row, and initially both the players have zero score, right? So in this question, score is associated. So let me take another color. So this question is similar from the previous one, that both the players have some scores. In starting, initially both have zero scores. Now, player one can pick same the first element or first two element or first three element. And after that, player two can also pick the first element or first two like this. So for this question, think in a little different approach. Like suppose I'm taking a difference, taking a difference variable, right, which is initially at zero. Now, if player one picks any element, so our difference will become if he picks the first A. So his difference will become plus A, right? Now, if his opponent picks the another suppose that is B, so the difference will we need to subtract the D from the difference, right? Because this difference is for player one only. And in the end, we will check if our difference is positive. Suppose if our difference is positive, that means player one has greater score. That's why his difference is positive. And if it has negative difference, then the player two must have better score, right? So we can use this difference very well for checking if player one will win the game or player two will be winning the game, right? So now, suppose we have index I, right? So player one will have three possible moves. That is, he can either pick one I, right, or he will pick I plus one and I both, or he will picking we'll be picking I plus 2 index, I plus 1 index, and the ith index as well, right? So after going to any moves, then the turn will be of the opponents, right? So player one will be going with that move that ensures that players go with the minimum, same as the previous one. So if I show you the approach, it is like first we take a recursive call. Inside that we have index state, right? Which will be starting from 0. And the base case is simple. If our index size become like if our index become greater than the size of array, that is I becomes greater than the n, we will simply break the loop because there is no other loops left. Now this look at the take, that is 0 here. Why it is 0 here? Because we'll have three more. We can either pick one. So we are taking a for loop and running up to 3. And in the first loop, we are adding only the, like, if we drag on this, that for loop. So inside that for loop, we have take equal to 0 initially. So in first iteration, the take will be implemented to p plus I, or in the code that is st, right? Because we are adding, I can clearly see here, we are adding that index I will be 0 and index that is passed on the recursion, right? And for this is for I equal to 0. For I equal to 1, uh, we will add take, will add the next element to the take variable I plus 1, I plus index plus 1, right? Index plus 1. So here, this element is already there in the take, and we are adding one more element. So if we are going with this case, so our take will contain the value of both the element, so the I1 and the I plus 1 both. And for this, the take will contain the all third element inside the variable. So after taking all the three possible cases, we will be taking maximum amount of value, because the opponent will move the best optimal move, right? So we'll have to pick something from our take, right? So after like this is our take, right? So we are subtracting something minus from take. There is another recursive call. So up to this is our move, right? And we are subtracting our opponent move. And this opponent move is simply nothing. It is a recursive call that is uh, using used by both the players. That is this recursive call. So it will ensure that it will give the best possible move, and we are subtracting it from our current score. So if this is positive, then we can easily win the game. Otherwise, opponent will we like if our difference is negative, then opponent will win the game. Right. So this is about the this problem. And if both the scores are same, so we can return tiger. And in normal DP, we use -1 right for assigning DP. But in this problem, we are using int minimum because uh, the this take minus DP are using int minimum. These are the points. Like we are initializing a state that will store the maximum score. Base is that is if our index size becomes greater than our array size, so we'll return 0. And we have a transition that we can either pick 1, 2, or 3 stones, right? And return values are also there. And, in this problem, the time complexity will be of only one state, and the transition is also of 3 only. So it will be close to 3 or 4 and something. This is the time complexity for this problem. Let's move to our next question. It is in this problem, Alice and Bob takes turns playing a game. Alice starting first. Initially, there are n stones in a pile. On each player's turn, the player makes a move consisting of removing any non-zero square number of stones in the pile. And if player cannot make a move, he or she loses the game. Given positive integer n, return true if and only if Alice wins the game. Otherwise, will be given with n or integer value, right? And game is simple. Alice and Bob are playing this game. This n is the total number of stones that are given, and in one move, Alice or Bob can pick uh, a number of stones that is a perfect square from n and remove from the suppose this is a bag or table something, and we need to remove that number of stones that will be picked by the players. So suppose if Alice can pick what? He can pick 1, 4, right? Because we need to pick, we can pick only square numbers of stones, right? Players make a move consisting of removing any square number of stones. So any player can pick 1, 4, or you can say 9, like this, right? So I will be dealing with this question. If I show you the test cases, that is, suppose they are n equal to 1. So Alice can easily pick the 1, and there are no element left, and it becomes 0. So Bob will left with no moves, and Alice will easily win the game, right? So Alice wins. A wins. Now, if I talk about the second test case, that is n equal to 2. In the first case, Alice can remove only one stone because uh, there are only 2 stones there, so she cannot remove 4 stones from 2 stones only. So she can remove one stone. So our left stone will be 1. Now Bob can make a move also. Um, he can remove the remaining stones. So and will become zero. And after that, there are no moves. So this move is Alice move. This move is Bob's move. So there are no moves for Alice. So Alice will lose the game, and Bob wins the game. Right. So now the question is how will be solving this question. So now we need to check uh, if any of the next move is losing, then we can surely say that we are winning. So suppose, uh, and like in this case, let me go to the code part. So for states, we'll be storing n because n is the only dependent variable here. So and the base check will be same, like if n becomes zero, there are no moves for both the players, so we'll be simply returning zero. And transition is simply like this. Try removing every valid squares number of stones. If any of this move leaves the opponent in a losing state, then current player wins. What is saying is, so we'll be exploring all the possible moves. Like in starting, suppose we are losing. Like so, we take a bull, just any flag or something. Suppose I'm taking F, and initially I am supposing that I am losing the game. Right? Now uh, we will explore the all the possible moves that can be taken. Like I am taking a for loop, and I will be running up to M, and will be checking for only squares. Right? So if I write except for loop, will be like this: I equal to 0. I will be starting from 1, and will be going up to less than or equal to n, and incrementing like this. You can clearly see here in the code, starting from 1 and going up to 210 and checking if any move is present that uh, pushes our opponent to a losing state, then we'll pick that move. So we'll gonna win this. Like in starting, we assume that we are losing the game. Now we'll explore all the moves and check whether if any moves present that is a losing state. Losing state in the problem is that if opponent will take that move, he or she will gonna lose that move. So if any move in all the possible case is returning false, so we can forcefully assign that move to our opponent. So if any move returning false here, our move is that like I we are picking any I, like so we'll be subtracting first from n because there will be only this number of element remaining. Possible case is giving false. That means we can force our opponent to go and take that move, right? And we can then we can easily say that we can win the game. So we'll be making marking our flag variable as true, and we'll simply break the for loop. Suppose if we can't able to find any possible move, so we'll simply return false because there are no moves that can guarantee that we will win the game, right? So if any move is present which forces the opponent to lose the game, we'll pick that as only and return the answer, or you can say this flag variable. So you can clearly say, see here, we are doing the same thing. We initialize the integer answer, so flag variable, and after picking any of the I, we check if that I ensures that our opponent will lose the game. Then only we'll pick that I and break the for loop, and then we'll return that answer. Or in the case, we can clearly store the in the table, right? So this is about it. And if we talk about the time complexity, it will be O of n because there are one state that is n, and if we go to the transition part, there are root n maximum we can have root n transition. So the time complexity for this person will be close to n root n, and which can easily pass the given test. Right. So I hope this question is clear. And now next part will be taken by first. So if you have any doubt, you can ask. Otherwise, first will be taking the next part. Thank you.
So I hope my screen is visible to all of you and I'm audible also. So we'll continue our discussion about the game theory. From this part, we'll now continue to the more means earlier we discussed how game DP works. Now we'll go into the actual XOR part and mirroring that happens, that is symmetricity in general in games. So first let's discuss what are the types of games like combinatorial games. So first are simple games. You can see here. So simple games are what? Simple games are nothing but basically the games where the answer is deterministic. Like if there are n piles and if both of the players, that is A and B, are equally smart, then the game's result will be determined by how we play it, right? That is only position determines the game, not the different set of rules. Okay, so two players play alternately. That's what simple games are. In general, also different types of game can have two players playing alternately, but in simple games there are always two players. So complete information, no hidden information, and no randomness. Both players play optimally. That is, both are equally smart. There's not any kind of knowledge gap or any other thing. And the game ends in a finite number of moves. So it's like if one player can't play a move, then he wins or loses depending on the type of game, right? So if A or B are playing, and if any of them cannot play a move, so they lose or win depending on the game. So after that, there is normal play and misery play. Okay. So what's normal play? When there is the last set of move, and A picks the last set of move, then A wins. If he picks the last set of move, right? So A wins, and B then loses. If it we are playing normally, this could be the normal game. Else, there can be a misery game where the one picking the last one loses, right? So it's like the opposite of normal game, but not in the sense it's completely opposite. It's just in the theoretical sense. Last move loses in misery play, and last move wins in normal play. This is only the thing we need to remember, because sometimes if you miss that point of detail, we will get into trouble, right? So then there are two types of games: impartial and partisan. So impartial and partisan, whatever we have seen till now, are impartial games. Okay, impartial games are nothing but there is no difference, means the legal moves only are from the player and every game state, right? The rules are independent of whose turn it is. That is same set of rules, and there is no partiality among the players. Both have same IQ also. Both are both have same ability to pick the moves. So these are the games we are going to discuss. All the simple games and the games that are asked in, means these type of questions on code forces or competitive programming, are impartial games. And what are partisan games? Partisan games are the same thing, just instead of uh, here different set of moves also depend on the position of the players, right? So it's a little bit different. Yeah. So here example, we can see chess, or we can see checkers in that sense. So here what happens? The player is playing a game, and the moves also depend on what the position of the board is, or like in case we can see Sudoku, or we see this tic-tac-toe. In general, the solution to these types of game that are partition are recursion and backtracking and require much more efforts, while the impartial games can be formed usually solved using Gandhi or Zor this way, right? So this was the difference. So partition games require what? Recursion and backtracking. The games which we have seen usually n queens and all, you need to check every state and every position too. So this is a little bit different, but for the consideration sake of game theory topic, you only get to have impartial games. That is only thing we have till now, is both of them are equally smart, and then we'll start playing the game. So let's start. We have already played game DP, basic things, right? So now let's introduce our new topic using this question statement here. There are m piles of stone where each pile consists of n stones. Okay, m piles of stone, and each stone is each pile is containing n stones. Okay, so then there are two players playing the game, A and B, right? So what happens if think if there are n piles numbered from here to here, 1, 2, 3 until n, and if they have some height like this. What we have mentioned here is a similar type of question based on the same logic. It says us that from a pile of height m, yeah, so from nth pile, we take a factor of n and means replace the height of m from it. Like this consists of height m, the ith pile, and will represent, means replace the height of it with a factor of m, right? Like think if m has a factor xy, we will replace m with x or y. So now what we see, look, our biggest clue is all the heights here are containing m height. right? Okay. So now all of them are containing the same height. So what we can do is, if we take a value from this and replace it with a factor y, we can always mirror it in another uh, whatever we can say pillar or mth pillar, right? So what we can do is, if we have got a pillar, this pillar, we can always mirror it in another pillar. If we have reduced its height to like this certain level, we can always repeat the same game and do the same move exactly here and cancel out each move at each time. Only drawback is, we can only do this until there are even number of uh, what we call it, this pillars, uh, m heighted pillars, right? Only until they are in a number that is odd, sorry, that is even. You can only mirror till that time. If there is an odd number of piles, then what do we do? That this height is there, then we cannot mirror it, because the person can pick the whole pile and there won't be a mirroring option available. That is, we cannot prove by symmetric way to get an answer, right? So what do we see just here? It's a very basic thing then. If we have an even number of piles, that is our observation, that every pile has an identical partner. And if we have even number of piles here, so when Alice or A picks one pile, Bob performs the opposite same move on its paired pile. And if A picks 15 or any factor of 15, B picks 15 or the same factor of 15, what we discussed just now, and B matches every move. So we always see that what B picks the last, B picks the last stone, right? Now what? Thus A is the loser. A loses, B wins. And if the number is odd, then what happens? Look, what we can also say is here, that if A is playing and there are odd number of piles, okay. Now A picks the whole pile, okay. So this pile has become emptied. So for B, how many piles remain? Even number of piles. So for B, if even number of piles remain, we saw from this example that whenever an even number of piles remain, the opposite opponent wins. So for B, even number of piles are remaining, so it's generalized that A will only win if they both play optimally. Okay. So this is how we can introduce our next game, that is NIM game. Okay, for what a NIM game says, that there are n piles, right? And all of them contain value like AI. All n piles have from I 1 to n, right? From each pile, anyone means from any one of these piles, one can pick a value like this, a value, and A1, A2, A3, A4, A2, both can be same or different, doesn't matter. That is, we represent the values in form of stone piles, right? So V1 and V2 exist there. And if the person who is the last picking wins, so if B picks last, B wins. If A picks last, A wins, right? So from the previous game, what we saw, that we can always try to have a mirrored approach. What I mean by mirrored approach is that if we make a disturbance of x in a pile, right? If we make a disturbance of x in a pile, if there exists another pile where we can make the exact same difference x, then we always get our last move. Then we always get our last move, right? And if we make a difference x and it cannot be mirrored or it cannot be made in a symmetric way, so we always get our last move. one loses. Okay, it cannot be mirrored then, right? So what we do, we check that if any value can be mirrored in step, then we get our answer. So you remember, if x mod x in a if we take the XOR of it, it will always be 0. So any change in this value, if mirrored in another value, will result in a 0 XOR. Right? That is, the XOR sum is 0. So if taking for the all of the n piles, what we try doing, we try mirroring for all the n piles. Let's consider a case here, like this is actually very basically, uh, the only solution for this exists in only XOR, XORing all the values, but we'll try to have a look how we are getting the answer. Consider here we have piles as 5, 5, 3, and 3 value. So the piles of stone contain these values. Okay, this, right? So now think we have made a change and we have picked a 3, right? Leave if we have picked a 3 or not. So let's consider if we have picked 2. So 2 is what? This sorry, this in binary representation, and these are binary representation of these values. So if we pick 2, 2 of one pile, then what we can do, if we have picked 2, that is this one and another 0 from any of those piles, either we can mirror it in this pile or in this pile as it is mirrored. This is also a mirror of 2. So we could have picked here. So it's reflected. Now what remains here? This one and this one. If the in another play there is a value that is picked from these two, we can always mirror in this one. I've taken a basic example for this general case, and then it can be mirrored in this one. Like this mirroring of sort, we can always get our value and see we are always forming pairs of one and zeros. And if we look, the value in the same from here, so we can always get the value in the same from here. So it, if the overall XOR sum is same, it does not affect our final answer also, right? So here, look at this case example. We cannot mirror the values. So look, we cannot mirror the values here. This one mirrors itself, but for this row, there is no mirroring, right? So let's see how we can make the approach cleaner. Now let's look what are these values. What are these values? Okay. So it's decimal, means binary representation of the values 18, 22, 14, and 22. Yes. Wait a minute. Yeah. So these are the values. These are the representation of the values. 18, then it's 37, 22, 14, 37, 22, 14, and 47. I have colored here in the same way which of these value can make a possible mirrored pair for the another number. So one makes a mirrored pair for another one. Look, if we have now, I'm telling first what I mean, and one makes for this one, and then one for this in the red color, and then another one for this. So what I meant was, if we have got a 10-10, right? So we can always mirror any value thing if we have just reduced one from it. Sorry, it is two actually. So it becomes what? 0, 1 and 0, 1. Right. So the value of the XOR is always same. What I can prove from this, think I have A as the original file's value, and X is the change I have done, and then B and X is the same change I have done in file B, right? So we already know that X XOR X is equal to 0. Now look what happens. It will be A XOR B, then it will be A XOR X, wholes minus, as XOR is commutative, plus 0. So as this value is already a mirrored version of itself, it should be 0. And to win, this also value should be 0. So we check how the whole sum is getting to be 0, right? So this is what basically nim is. We take all the values and check for a change, that is delta x. Can we form another change, delta x, thus getting a XOR sum overall 0, right? If XOR sum is 0, we see all the moves have been perfectly matched. And now what happens? If XOR sum is 0, all moves have been perfectly matched. And now then second wins as he mirrors all the move and is the last one to pick, right? Or not pick, even it's in his favor. Or else, if XOR is not equal to 0, it is first, right? So now let's see another version of the same nim problem. Look, it's misery nim. We have already discussed what misery games are. That is the last one to pick loses. Okay. As the rules of the nim game remains the same, what do you think would happen? You would mean that the taking XOR of means taking total XOR sum and then check if it's 0. Then for it, the cases should be reversed. We should get a value second, and if it's not 0, this we were getting in the normal. So if it's 0, we will get first, else we will get second. This is what you meant, right? Means normally would think in general. Okay. But this does not happen actually. Actually, we see that except a special case, we'll discuss the special case later on. If we have different types of cases, right? So we can always form a value and keep mirroring as many as possible. If A picks a number here, B may not necessarily pick the same number. Rather, B will pick a completely different number. And then even A can pick a completely different number. Different number. Like this, the game goes on, and then we can make another set of move that can be mirrored. And as the nim game says, that if XOR sum is equal to 0, B always wins. Now let's consider the case. Take 2 comma 2 comma 1 comma 1 is the misery example that we were taking. Okay, so what do you think if A picks 2, right? If A picks 2, then does B want to pick 2 right away? No, B will pick 1. So the number of remaining values will be 1 comma 1 comma 1. And now A, what he can pick? He can always pick from one pile. So we'll pick this. Then B will pick this. Then again A has to pick the last one. So actually, even if we think that he wins, he loses. Now think if there are again 2 comma 2 comma 1. If A picks 1, B will pick 2. Then their remaining values will be 1 comma 1 comma 1, right? So these are the values that will be remaining. Okay. So now look what happens. A picks again. A picks this. B picks this, and again A ends up on the losing. Okay, he could have also picked 0, but the answer would have been always the same, except for a general means this test case. What we were talking about, 1 1 1 1. Like the first problem we talked about, m n piles of height m is the same where m is equal to 1. Here, as he can always pick a value only 1, so this will alternate. So if in a this game is called misery, right? So here what happens is if we have a XOR sum as 0, we can always mirror. We can always mirror and still B wins. Okay, except a special case, except a case where the m is equal to 1, then we have to check if m percent 2 is equal to 0. That is, m is a multiple 2 or even what we call, then A wins as B will be the last to pick, or else B wins. The code is very easy, so I have not mentioned it here. But you can see case 1 is at least one pile has a size greater than n. That is, all of them don't consist of only 1 1 1. So the XOR is 0 is losing position, and XOR not equal to 0 is the winning position, just like normal name. But if all has pile size 1, then odd numbers of pile and first player loses, and even number of pile, the first player wins, right? So it's very simple in the sense. Only thing we have to keep in mind, that is keep in check, is this mirroring, or for the last case, right? Let's look at one another game, that is Nimble. It is a very popular game. Here it says that there are n boxes like this, and all of them have some points here like this, and one can move any means from any of this box, one coin from any of the boxes to its left, right? So it's only to its left one can move. So now what we can see, look, if we are at 0, then we are of no use actually, because at 0 cannot move to left further, right? Also we see, if there are means in a box, if there are totally even number of coins, if I pick this one coin and move it here, so in the next step the another guy can make a completely similar move and move it here as well. So boxes with even value also do not actually help us, has no help. because its move can be mirrored with the same coin in that box, right? So we always have another step to pick, right? We always have one step. Now let's see if it has a odd value. Let's consider there are boxes and it has these values. Okay, there's box this, and now this. So this is at zeroth box. This is one. This is two. The box at two can put in value one or value zero. So all of these three can have value zero or one. So this represents what? At uh, a value that is 2, we can get two values to send the coins, right? So it's similar to the heap size we were talking in this nim game, right? So we can either put it here or we can put it here. If we put it here, we can replicate using this value, and then if we put it here, we can replicate using this. So even we reduce the even number, we only focus on the odd coin. So let's see what happens for the odd coin. So if we put it here directly, right, to its left, it can be mirrored and we can put it to this place. Instead, what we can do, we can directly put it here also. So there is one losing state and there is one winning state for this game. So how we find the plan? It's very similar to as the game says its name is Nimble. So there are for two, there are totally one and zero possible states to jump, right? So its heap size is actually two. So for each pile, we see how many heap sizes there. We already know the XOR of the heap. XOR of the heap equal to zero is when the first person wins, else it's when the second person wins, right? So what do? We take XOR, right? We can see the approach here. A coin on zero cannot move, and coin behaves like an independent heap of size equal to its position, right? We take XOR of all the values. Yeah, coins on the same square cancel in pairs. So what we saw earlier, that is the even coins cancelled and the odd ones only one coin stayed. For that case, what we see, we can take XOR of the values on the position. That is, we take position of all odd number of coins, right? Then XOR equal to zero is the losing position. That is the losing position of the coin. And one is the winning position, right? So this was again a very simple question. So there's another game called Staircase Nim, and there are many more games. You can try out this Staircase Nim at your own. It has a very similar concept, right? So where the number of steps are the values you can put on to the left. So you can search for the question and try it out yourself. And henceforth, let's discuss what Grundy numbers are, right? So Grundy numbers lets us convert games like game DP based games directly to NIM based games. How it does it? Grundy is based on MEX, and we know what's MEX. MEX is maximum excluded integer or value, you can say. So it's a set of whole numbers 0, 1, 2, 3, 4, like this, and the first number not existing in this set is the MEX, right? So if we have a set consisting of only 0, then 1 is not existing there. So 1 is the max. If there is 0 and 1, both are existing, then the max will be 2. Think if a set has 1 and 2. So the first number not existing is 0. So 0 will be its max. Now, what does Grundy number of a state represent? It represents the type of numbers here. That is the type of states here. The state, if the Grundy of a number is 0, that is we are put on a losing state. If it's non-zero, then it's not losing state, right? Let's discuss a question and we'll get to know Grundy and Grundy theorem too using this. Now we have already known what's max. Now see that how Grundy number is formed, right? So look, what do we do? Let's take this question for here as there are n piles of stone. On each turn, a player chooses exactly one pile. That is, again, we are thinking in the same name direction. And he may remove one, two, or three stones. But then you get an idea that we are talking about the DP of the same question. That is 1, 2, and 3. Then we keep minusing all of them and calculate all the states and store it in a DP. And then we can check if not of each state, it gives us lose or win situation, right? So instead of that, what we can do, we can define the Grundy value of all the n piles, right? If we had used the DP approach, it would have gone in O of n square, as you had already seen earlier, but we cannot afford that. So for n piles, we define the Grundy values at g of state. G of state is equal to the max of the states this state can reach. So it will be Grundy of state, this state minus 1, like this, minus 1, minus 2, and minus 3. Now we already know a situation that is winning for Bob. Win situation for Bob is what? If it is a situation losing in next step for Alice. Okay, so this is the current state we are talking about using Grundy, and this is the next state we are talking about using uh, this is the next state we are using about by deducting minus 1, minus 2, or minus 3. Now, what we saw earlier, if Grundy of 0 is 0, means Grundy of any value is 0, we are in a losing state, right? And if it's not 0, then we are in a winning state. So if state minus 1, minus 2, or minus 3, any of them gives us a value that is 0, means that is non-zero. Non-zero, so let's consider 1, 2, 3. Then all of them are winning positions. So winning position for Bob is actually losing position for Alice, as this is the current state we know, and this is the next state we could have possibly reached. If we know 1, 2, and 3 are the Grundy values, we could always reach a value that is positive and not equal to 0. Hence, we can always get our value of a winning state for B. That is, we can always win in such a case. But if we had got a value that is 0, 0 is losing state for B, right? So 0 will be a losing state for B, so it will be winning state for A. So if we have got a value 0 at in this case, then the max would always be greater than 0. If we have got a 0, then max would always be greater than 0. At least this is the answer we know. So for each state, we have already defined our Grundy already with the formula above. This state minus 1, 2, 3 is max, right? So now what we do, as we have these n piles, we know we can get some Grundy value, 1, 2, 3, 0, right? We have already seen 0 is a losing state. But now, as we have n piles, we have n Grundy numbers. If for one pile we are talking, 0 would have been a losing state. But if we get a Grundy value 1, we can actually mirror it if we have another Grundy value 1, right? So even if we have two Grundy values, we can always mirror it using different piles. Similarly, if we have two, means even cancelling out Grundy values of 2, we can always mirror it using the same. So it turns out to be the same thing as we saw in NIM. That is, for one pile we defined our max this way. One pile we defined our max this way. And Grundy number, if it was equal to 0, it was a lose. If it was greater than 0, it was a win. Right. Now for n piles, what we do, we have Grundy numbers G1, G2, like this going on, Gn, right? And now if we take the XOR, we can see the mirroring happen again. And we can also see if its XOR value is equal to 0, player B or second player wins or it's the losing position. And if XOR is not equal to 0, then it's for player A. That is the winning position. This is what the Sparge-Grundy theorem says us. Now we have discussed this classic Grundy theorem, Grundy DP problem, similar to that. That what we see the final answer as XOR of both all the Grundy numbers is Sparge-Grundy theorem. That is for a Grundy game. The means XOR equal to 0 by XORing all of the values of Grundy of game 1 for first pile, second pile, all individual piles, and game K, right? Then we see what we get. If we get 0, we are at the losing position. If we get not equal to 0, we are at the winning position. So Spark Grundy is nothing but converting this max. How we were getting max? This always tends to a winning, and if 0 is not present, then it tends to a losing, right? So this is how we do it, and this is all about game theory. We can form similar questions based on classic Grundy or NIM game, but overall concept remains the same, that is mirroring, and the approach is also the same. So that's it for game theory. Thank you all. I will stop sharing my screen. If you have any doubt, you can ask me.